Today I shall discuss the Heisenberg uncertainty principle. This principle is one of the pillars for the development of quantum mechanics. Actually, in quantum mechanics, this uncertainty, non-locality, and some results of this quantum mechanics is found to be contrary to our intuitions. These are the main features of this quantum mechanics. Heisenberg uncertainty principle is one of them. It is not possible to design any instrument by which, with the help of which, one can determine both the variables of a pair of conjugate variables. For example, if we try to determine this position of x, then it will create some error in x, and this delta x, suppose, is the uncertainty or the error in determining the position of the particle. Then conjugate variables of this position is the momentum. Then momentum automatically induces some uncertainty in its determination, and that is, suppose, del p x, and these two, product of these two uncertainties must be greater or equal to half h cut, and this is the Heisenberg uncertainty principle. Any two conjugate variables one cannot determine accurately and simultaneously. Other variables also we can call other conjugate variables, del p phi, angular momentum uncertainty, into the uncertainty in azimuthal angle. This will also be equal to or greater than half h cut, or del E into del T is greater or equal to half h cut. In general, we can say del P into del Q is greater than half h cut, where Q and P, these two are the conjugate variables along the same directions, along the same degree of freedom. If we discuss more elaborately with this first one, then del P x into del x, since h is very small, so we can write almost equal to h. It is possible to determine the position very accurately, separately. It is also possible to determine the momentum of that particle along this x-axis very accurately, but it is not possible to determine these two simultaneously and exactly beyond a certain limit. If the position moves along, if the position of the particles moves along this x directions, and the momentum along this y direction, then these two are not complemented, these two are not the conjugate variables. In that case, both the variables we can determine accurately. Say del py into del x will be equal to 0. Means both the x and py could be determined accurately, and the uncertainty 0. We can approximately formulate the Heisenberg uncertainty principle. Say, suppose here is electron. We like to locate the position of this electron. And here is one instrument, one microscope, and one by this microscope. This microscope is placed to determine the position of this X, and this is the lens, and this may be the eye, and this is the electron whose positions we try to locate exactly. And for determining the positions, one have to use another agency, and that is called the light. And light is used. This is the h nu. Light is composed according to the quantum mechanics, consisting of the photons, and each photon is having the energy h nu. So whenever we determine the position of this electron, there occurs the position uncertainty. Uncertainty in position depends on the frequency of this wavelength of this light used. This one is almost equal to this lambda wavelength of this light. As for example, suppose here is two spots, and two spots you like to visualize through your eyes in presence of this light. These two, suppose these two are difference between the distance between the two spots, say del x. So in order to find or locate these two distinct spots, one have to use the light whose wavelength must be shorter than delta x, or delta x must be shorter than this lambda. Lambda is must be smaller than this delta x. The maximum limit, we can say, this is uncertainty in positions. So whenever this light beam or this photon strikes this electron, this electron gets recoiled from its own positions with this change in momentum equal to the energy momentum of this photon. So this delta px, change in momentum of this electron occurring due to strike of this photon, is equal to this px. Px is the momentum of this electron, momentum of this photon which is imparting to this electron. And this one, according to this de Broglie relation, it is lambda, it is h by lambda. So delta px and into delta x, if we try to find out this product of these two uncertainties, then delta px equal to h by lambda, and this delta x equal to lambda, and it is almost equal to h. So this is a very approximate formulations of the Heisenberg uncertainty principle. If one tries to, if one can try to determine the positions very accurately, then lambda should be shorter. When the lambda or the light, he will have to use of shorter wavelength. Whenever this lambda is small, then delta x is small. Whenever delta x is small, delta px becomes much greater, as the momentum of this photon will also be increased, and there will be much more recoil, and then there are more uncertainty in determining the momentum of this electron. It is not the limitation. It is not the limitations of this instrument, or it is not the limitations of the experimentalists who are doing this experiment. It is the inherent nature. This limitation is the inherent nature, inherent property of this nature. A very simple example I can give you. Say a dark room, and on the floor of a dark room there is a table tennis ball, and there is a table tennis ball in a dark room. No light is there. One is asked to locate the exact position of this ball. He actually, how could this person can determine the location of this ball? He will go on by grouping or searching by this hand, and whenever this hand will touch this ball will shift from its own position. So without disturbing the position of this ball, it is not at all possible to determine or to locate the position of this ball. This Heisenberg uncertainty principle breaks the Newtonian mechanics, Newtonian laws of motions. Actually, in Newtonian laws, position and momentum, or say velocity, could be determined very accurately. And whenever a macroscopic body moves, it will give say a track, and this track, whenever a track is definite track will be there for this macroscopic bodies according to this Newton's second law of motions. So whenever we are considering the subatomic particles, there is a position. Suppose this is the position and this is the px, and there is an uncertainty, and there is uncertainty in position and momentum, and so definite track is not found for these subatomic particles if it obeys this Heisenberg uncertainty principle. And these possibilities, this Heisenberg uncertainty principle also invalidates, or you can say rejects this Bohr definite orbit motion of this electron in the hydrogen atom. And we can show very easily that suppose delta px, you are determining the position, you are determining the momentum of this electron in a first orbit, and this is the nucleus. So this is the nucleus. Electron is moving in a circular orbit by this fashion, and whenever it is moving, say this is the r. R is definite, or suppose n equal to 1, or the first orbit of this electron. Then r is fixed, and also the velocity of this electron moving in this orbit is also fixed. And r and velocity having a definite formula according to the Bohr theory, and these two could be accurately known, but it is not possible for this invalidates, this rejects these soft values of this r and p velocity or mv by this Heisenberg uncertainty principle. If we consider the delta p momentum error is about 0.001 or say equal to 0.1% in determining the momentum. This is the error of this momentum. Then we can show the delta r, the uncertainty in the radius of this orbit is equal to 3660 angstrom, whereas this r equal to 0.53 angstrom, and the uncertainty is found to be this one so high, then we have much doubt whether this electron is at all remaining in this hydrogen atom or not. So this orbit is rejected, and in quantum mechanics this orbit is replaced by the orbital, where the possibility or the uncertainty is incorporated, and it is the contour or the region at which the probability of finding this electron is maximum. In case of this third, in case of this one, it is not the delta T is not the uncertainty determining the or time uncertainty. It is actually a duration of, suppose this is the hydrogen atom is present in equal to part in the first orbit. So delta T is the lifetime of this electron to stay in this definite orbit or stationary state in this state. If we consider the delta T in the stationary state, we can see delta T equal to infinity. Means this electron will remain in the first orbit for a indefinite period of time unless it is disturbed by some other sources. So whenever delta T tends to infinity, delta E equal to h by delta T and equal to h by infinity, and this is equal to 0. Means there is no uncertainty of this the energy of the electron while it is moving in this particular state or particular orbit. So this is why this orbit for this hydrogen atom we can call this stationary state. This is the permanent state. If the energy is supplied in the form of photon, then it will shift to this another orbit, this second orbit. This electron will shift to this another orbit, and this is the excited state of this hydrogen atom. And in this state, the hydrogen atom remains for a very, very small period of time. Means lifetime in this excited state. Almost equal to 10 to the power minus 8 seconds, or like that. Since the lifetime here is very small, there is a much more uncertainty in delta E. Means this electron in this hard state energy is very highly uncertain, and it comes back to its initial state to regain this stable. This uncertainty is delta x. Delta x uncertainty is measured as the standard deviation or RMS. RMS root means square deviations. And delta x equal to square of this mean square of this position minus square of this mean position. This delta x, the uncertainty position, is calculated as mean root mean square deviation, and it is the mean of square position minus square of this mean position. And similarly, delta px is also equal to root over of this px square and mean position, mean of the square of x component momentum minus the px square of this mean x component momentum. So this is all about the Heisenberg uncertainty variable. It puts a limit for the determination, and Einstein, the great scientist, is not a believer of this Heisenberg uncertainty principle. He actually states that the science, the glory of the science is for the determinations of the accurate values. So why the uncertainty is coming? But experimental results derived from this quantum mechanics is found to be so accurate that no scientist, even Einstein, would not deny the importance of this Heisenberg uncertainty principle. This is all about this principle. I thanks to all. I give thanks to you all for watching this video. Okay. Thank you again.